Well, thank you for coming, everybody. My name is Mike Gretzinger. I'm the research coordinator here at Farming Smarter. So it's my job to make sure that plots like this end up in the ground. And a special thanks to Ken at the back there and Jamie, our assistant manager, for putting these ones in. They spent probably an entire day getting the monosem set to every proper spacing and getting all the residue figured out.
An entire day, Mike.
Yeah, it was.
This demo just about freaking killed me.
It's a lot of work went into these plots, and we couldn't be happier with how they turned out. They're probably one of the best demos we've put out. Sometimes we put a demo out and you don't see any differences, and we're going to walk you through, and you're going to see every little nuance that we could want to see. So we're really happy about that. Who's our corn experts in the crowd here today? Anybody? Anybody grow corn?
Mark.
Mark?
Right here.
Okay.
No wizards here.
I can pick on Mark a little bit then.
Grow it in a room.
Grow it in a room, okay. In a growth chamber.
Yeah.
Yeah. Perfect. Well, this is going to be out in the field setting. It's going to be a little different, but we'll see what kind of things apply. So I'm going to touch on our grain corn study. So we did a 4-year dryland grain corn project here, and we just finished wrapping it up, and that ended over the winter time. But I'm going to touch on the results of that, and then talk about kind of what we found as the most important results, and how we set the demo up, and then maybe talk about a few other projects that relate with the strip tillage machine and some of our deep banding. So to get us started, we ran a 4-year research trial. It was 3-year research trial. We had 4 locations: Lethbridge, Medicine Hat, Bow Island, and Vauxhall. We started with a variety trial. So we took a whole bunch of varieties from the Corn Commission trials, normally under irrigation. We brought them into the dryland setting. We wanted to see which grain varieties would perform, whether or not everything went to maturity. And for the most part, we found that we achieved maturity for all those dryland, or for all the varieties that we had, and we saw that the heat units didn't make a big difference on yield. So when we averaged the different heat units, we had anywhere from a 2050 corn heat unit all the way up to a 2500 corn heat unit, and the graph going from one end of the scale to the other, there was relatively little change in the yield. But what we did find was that each of those points, there was a massive variation in the heat units. So why would that be? Or sorry, massive variation in the yields. So the big reason, what's that?
Variety.
Yeah, it really came down to the specific variety and the traits and how the company ranked their heat units. So every company has a slightly different way of regulating their heat units and coming up with those numbers. So when it comes to the corn heat units and selecting the variety, I think probably the most important thing is just to talk to that retail agronomist and make sure you pick the right variety according to all the traits and things that you're looking for. You can't just look at a number on a bag and say, oh yeah, 2050, that'll be fine, because you could have anywhere between 1,000 kg difference in yield on two bags of seemingly identical kind of corn seeds. So when it came to, I guess our next study was nitrogen fertility. So what we wanted to do was see what was the impact of nitrogen fertility on dryland grain corn. So anybody growing grain corn, or anybody growing grain corn across the street under a pivot, is going to put a lot of nitrogen down. How much background N are you putting down for something like a grain corn crop?
We're putting over 200 pounds actually.
200 actual, yeah, absolutely. We've got pretty high fertility here. We've got between 50 and 100 on some pieces, and we'll put another 100 or 150 down. Corn really likes the nitrogen, especially under irrigation. So what about back on this dryland piece? What do you guys figure our best yields came from? Okay, I'll go through the treatment. So we tried to find plots, or tried to find a piece of land that was anywhere from 0 to 50 pounds total available background N. And then what we did was we put down 0, 50, 100, 150, and 200 pounds. And then we had some treatments where we had 50 side banded, and then another 50 in crop, and another 100 in crop, and another 100 pound side banded with like a dribble banded in crop, kind of 3 to 4 leaf stage. So what we found was that in the dryland site, once we hit 50 to 100 available, And once we hit about 100 to 150 total pounds of available total nitrogen, then we were going to hit our 80% of maximum yield. So if we, in our zero treatment checks on 50 pounds background N, we saw a significant yield loss. But once we added a base of about 50 pounds to get us to 100 pounds total available N, then we hit kind of our 80% peak. And after that, the higher the N we put in, it didn't make any difference in overall yield. So we needed a significantly less amount of nitrogen on a dryland grain corn than we did on something like an irrigated grain corn. So we have two more studies, and that's where we got the most interesting results. So we had a population and row spacing study. So with our population and row spacing study, what we did was we looked at 20 and 30-inch row spacing. So those are the plots behind us. So these ones here are all on 30-inch rows, and the ones off to my right there are on 20-inch rows. And then what we did was we looked at the population effect. So we looked at 15, 20, 25, 30, and 35,000 seeds per acre. So when we seed something like an irrigated corn, we're usually doing on 30-inch spacing, 30 to 35,000 seeds per acre, high nitrogen input. So with that in mind, we talked to a few researchers, and we took a whole bunch of guesses from all the agronomists that we could talk to. And the best number that they came up with was about 20,000 seeds per acre on a narrower 20-inch row. That was what we figured was going to be our maximum yield. So do you guys have any other guesses whether or not that's what happened, or what you think it might be? How many seeds per acre do you plant in the greenhouse?
Yeah. Pretty thin to it.
Is there a seeding rate, or is it just one in a pot kind of
We
thing?
had 48 pots in the room.
Okay. So that doesn't really transfer over very well then. Okay. So yeah, we figured narrow rows and
corn.
probably
This is corn.
lower number. Yeah.
Yeah.
So, what we found was that the 20-inch rows really did make a big difference. We got 9 to 10% yield bump across all the seeding rates when we seeded on a 20-inch row versus a 30-inch row. So when we moved to the dryland, the corn really took advantage of maybe the more spacing between the plants, the better spatial distribution, and that's where we got our maximum yield. But what we found interestingly too was that 20,000 seeds per meter squared wasn't our optimal yield. We never found a maximum yield. We went all the way up to 30 to 35,000 seeds per acre, and our yields just kept going up. So I heard the other day somebody was seeding 45,000 seeds per acre on their dryland grain corn, and I'm not sure that they've found their maximum peak either. So usually once you get up to a certain seeding rate, your yield's going to start dropping off again. But we didn't find that. So we haven't looked at the economics on the seed cost of the corn, but definitely the higher amount of seed that you can put down, the better yield you're going to get. So at the low end, 15,000 seeds per acre on 30-inch spacing averaged us about 60 bushels per acre, which I think is pretty good for southern Alberta. We had 2 drought years, and that's compared to some of the other crops we got at that point, I think we did pretty good. On the high end, 20-inch row spacing, 30 and 35,000 seeds per acre, we're up around 100 bushels an acre average yield. So pretty impressed by those numbers. So the final study that we did was looking at the crop sequencing, and what we did was we set up canola, corn, lentils, mustard, peas, soybean, and wheat as precursor crops, and then we came in and we either cultivated or no-tilled our corn afterwards. And what we wanted to find out was the effect of the stubble residue and our residue management system on the subsequent corn crop. So what we found was pretty significant, and maybe maybe I'll give you this and then we'll take a look at these demo plots. So what we found in the conventional versus the no-till systems was that in a conventional system with cultivation, we got almost 100% perfect emergence. So we had 99% emergence, whereas in our zero-till plots, we were down about 84%. So we had like a 15% reduction in emergence from going in no-till. So when you were over Yeah, probably actually haven't been over yet to look at the monostem planter, but we put residue managers in front, and those are supposed to help move the trash out of the way and get better seed bed distribution. But even with that, we couldn't get perfect 100% emergence on our no-till. But what we did find was that despite that, we actually had identical average yields. So in the end, we ended up with an average yield. So we're going to take a look at these plots, and then we'll maybe talk about why that is and what's happening. So what we did was we set up a system of 5 plots. They're all at 30,000 seeds per acre. Nitrogen wasn't limiting. We packed it on. We've got, oh, this one says 20-inch spacing. Okay, I'm going to start here. This is our 30-inch spacing, 30,000 seeds, and this plot was entirely cultivated. We went in with the rototiller, we beat it up. You can see we've got really nice green, healthy looking plants. They're 1, 2, 3, 4, 5 to 6 leaf. All the emergence is really uniform. That planter did a really good job at spacing everything out. There's maybe only 1 or 2 doubles there, but I really don't see any skips. Everything's at the same stage. And you know, if I was an irrigated farmer, I'd be tickled pink about that crop right there. But this is our typical situation kind of here in southern Alberta. We go and seed research plots, and I see a lot of straw that's packed on this thick, right? So this is our extra trash treatment. We went and seeded it directly after, like we seeded this one and then this one right beside, but they had spread all this straw on top. So what's the most obvious thing that you see in this plot?
The straw.
Well, straw. Yeah. What do you see about the plants? I mean, yeah, you're missing some. They're 1, 2 leaf. You got a big gap right here. There's maybe another one here. Yeah, we put these in. They're not going to be used for anything else. So come and kick some straw around if you want.
Is that the only difference then, Mike? Sorry, between the two is just the trash?
That's it. That's the only difference. We just threw trash down on this one. So
would it have been less if you put it seeded if they had trash and you just seeded it right into the trash?
No, that's what we did here. Yeah.
Put the trash down.
Yeah.
No
Was the
trash
down,
sweepers.
But I guess what I'm trying to say,
yeah.
was the trash down quite a bit sooner, so it kept the soil insulated?
Yeah. When was the straw applied?
Yeah.
Early? About a week before we seeded.
Yeah.
So the soil had warmed a little before the straw, depending.
Yeah. I mean the idea is that this one that's been cultivated is going to get a lot hotter. It's going to take advantage of that. Corn likes that early season heat, right? It needs a warm soil for the seed to germinate. So, you know, in a irrigated world, I mean, this probably looks a lot more ideal. But in our research trials, what we found was that despite looking like this, after a month of weather like today, these plots ended up catching up and actually yielding about the same, right? So in our kind of southern Alberta area, despite how this looks, it's probably going to catch up. And you know, there's not a lot of guys who like to cultivate their dryland sites around here, right? So that's what
I think the reason is because the moisture is being held better in there.
I think so. Yeah, that was kind of our main thought.
How early was this? Like, I guess because
Not super early seeded. No, this was one of the later ones we did. What's the
yeah,
date?
I think about May 23rd.
20th or something like
Yeah.
that.
Do you know what sort of it is?
No, we wish we had
Not
done that.
specifically, but we did this study last year, and we put a soil temperature and a moisture probe throughout the season, and we were actually a little bit shocked at how much the residue will insulate temperature, but more importantly moisture.
Yeah.
So the moisture that it's the moisture it's not what it says, it's kind of what it says, it's what's being lost here.
Yeah.
So the moisture
Yeah.
it just takes off, it just disappears, and that you know, that's sort of that whole premise of our zero tilling. And that's also the trick though, is we can see with the planter and with cultivation that we get a bump in the spring because of the quicker soil temperature warming up. But so how can we design a system that kind of gives us the best of both worlds? And we're not there yet, to be honest, but you know,
We're getting close.
next
Yeah.
plot.
Yeah.
Sorry, quick question. I might have missed it. Do you get 100% emergence out of the trash as well?
I think no, I don't think so. Like
the same in the end. So is it?
yeah, that was surprising to us. So like in the study that we did, we only had about 85% emergence. So the lentils are a low trash crop, so we had almost 100% emergence on both of those. The corn hit us hard when we seeded corn on corn when it was cultivated. We're almost 100, but on our no-till corn, we were only about 70% emergence. Corn on corn, no-till. And then the wheat and the soybeans and the peas and mustard and canola were all about 80% as well. So it did have an emergence effect too. So that's probably, you know, actually goes to show even more the effect of that trash and that conserved moisture, because you had only 80% emergence, but you still ended up with that kind of equivalent yield. So yeah, that does bring us. Yeah.
You didn't have to have any fertilizer on it to seed it out?
It would have been side banded at the time. So we had about 200 pounds Bach round. Yeah. We put about
Starter phos.
15 pound starter phos, and
It'll
What
is too much phos in canola with the seed strips?
we're gonna get there.
With
Yeah.
Lewis's study,
Absolutely.
We've been pushing 60 pounds an acre with us.
Yeah.
P205.
Yeah, without any injury.
Yeah.
Now, we're not turning around and recommend you do that, but you know,
On a disc.
moisture makes the difference. But zero till, we tend to have better moisture all the time. So I've seen very little injury with lots of seed placement. Mike's going to talk about another project that is looking at addressing that, and that's deep banding our
Immobile
phosphorus.
nutrients. Yeah.
What about these two emergence? Like after you planted those two?
You know, we didn't keep a huge eye on it, but
No, you caught up to me there.
I don't quite remember.
That's like just later, just because
I
it didn't come out.
I think so. Yeah. I think
It's
we've
a little bit of
seen
both.
that.
Yeah.
Yeah. It's later, but it's just slower too at the same time. It
Yeah,
just
corn is so sensitive. Even a rain event with cold rain temperature will actually slow the emergence of corn. It's really a tender baby crop.
Yeah.
A few years back when we had the field school module, we actually went out and dumped ice and water on the plots just to demonstrate that effect. So that's why they're always talking about, you know, making sure the soil temperature is 10 degrees, yada yada, that same
Yeah.
old thing. Most people ignore it because we don't have the growing season to afford it. But you know, again, this might be another solution right beside us now.
Yeah.
So where's the line that kind of you say we don't have enough growing degree days in southern Alberta? Like Vulcan is the line, or is it?
well,
They're growing it in Edmonton.
yeah,
Okay.
yeah, and
they
they
have low heat unit stuff now.
yeah they're getting kind of extremely low heat units on the breeding side, and kind of that. Yeah, a lot of those places are limited just on they get that early snowfall or something like that, and then they have to worry about taking their corn off. So yeah, so we'll pop onto this next plot, because this is kind of where I've been leading or alluding to. This is kind of our best of both worlds system. So that handsome machine off to the side there is a strip till machine. And what that does, and the idea behind that, is we're going to combine the two systems. And it's not something new. They've been doing it kind of North Dakota type areas for quite a while now, but it's new to grain corn in southern Alberta and what we can do with it. So the idea is you just basically run a little miniature tilling machine right down your strip that you want to seed. And then so now we're looking at a situation with the best of both worlds. So we have all this soil, about 2/3, that's under conserved moisture, but then under each of our seed bed rows, we're having the same effect of the cultivator. So we've got nice warm soil. The leaf staging is all about the same. It's nice and green and robust and healthy. So we're thinking this is going to be a really good option for dryland type grain corn production. We did a few other demos just to show you what they look like. So we've got the strip till under our general no-till system. So this is with a heavy trash. This is just under a no-till system, and you can still see the big benefit compared to the one beside, which is our corn on the zero-till system. So we've still got the strip till there, and behind me we've got no-till. And this is what our plots were more like in the study. So they were a little bit behind in some places, maybe a little more inconsistent. That's something we find on our no-till crops, is it's harder to get that consistent emergence. So some of this is like at a 4 or 5 leaf, some is popping up at 3 or 4, some is at this big 5 or 6 leaf. So, you know, a big advantage to having a uniform crop would be to use something like this strip till machine.
So in these studies, was nitrogen the only thing that was kept constant, or that was varied?
Depending on the study, like we tried to hit 150 pounds total available N for all the other studies, just to make sure it wasn't limiting and to make sure we weren't having an effect, which...
You guys weren't going after micronutrients or...
No, we made sure to put down a good amount of phos, a starter phos with a seed too. And then seeding rates, I think we went 30 inches and reached 30,000 seeds per acre for all the rest of the studies. So unfortunately, it would have been nice to reproduce the fertility and the residue study and stuff on 20 inches, knowing what we know now, but yeah. So if you were going to grow grain corn, dry land, like what do you figure? What are you going to do to manage all this stubble? What are some options to dealing with a field like this besides strip tillage?
You mean like pre-seeding?
Sure, yeah, pre-seed or year before, even in the fall before, I guess. I know.
Bale the straw off, drop it and bale it, or
chop it and bale, it's one option.
on your corn planters.
Yeah, we've thought of chopping and baling as one. Vertical disking, just running a flail mower through it. Obviously cultivated or no-till in, but ideally something to manage the residue. Where you're going to put that row is kind of #1 priority for getting good corn establishment. So that kind of brings us to another study that we're working on at a Smoky Applied Research and Demonstration Alberta Demonstration Association in Peace River, and that's a deep banding immobile nutrients project. And so what they're doing with that study is we're going in ahead of the crop and we're deep banding phosphorus, potassium, and copper at 5 to 6 inches down, and then we're going back in and putting the crop in over top. And the idea is that immobile nutrients, we build up a stratification in the soil, so you've only got phosphorus stratifies at 1 to 2 inches down because you're always seed placing your phosphorus, and then it's not available lower down to the rest of the root zone. And so what we want to do is put it at a 3 times rate, deep down 5 to 6 inches, so when we come back in subsequent years with subsequent crops, we can build that phos back up and make it more available to the plants. So what we thought was a really good connection was if we could take this deep banding and we could take this grain corn and kind of bring the two together, because we've already seen the benefits of strip tillage, and we've seen you get the benefit of having all the residue plus the benefit of the cultivation. So if we were looking at something like deep banding, we could go ahead and deep band all of our nutrients in the fall and then come back in the next spring and put our corn right on those rolls and follow it in. So then it would already be kind of pre-cultivated for us, and we can come back in with our corn and put the corn right in those rows. So it's something interesting we're looking at doing. So
what's the pH in those studies up there, like of the soil?
The pH, it's really different in the Peace River area. They're really deficient in potassium and copper, whereas here we're a lot more deficient in the phosphorus. pH there is what, like 7 to 8 range. Like we're about 7.8 or so here, 7.4 to 7.8 for the most part.
So would you worry about just the phos being tied up by deep banding it that deep? Because your pH is just going to get more intense the deeper you go, right?
Yeah.
It's in a band though, so you kind of are protecting it.
Right.
Yeah.
So that is true though. Like you have to be careful with fertilizer being tied up in the soil.
Yeah.
And that's part of the premise with the banding component.
Yeah.
You'd probably still want to do a starter application, but the theory then is that we're going to put 3 years worth of phosphorus down all at once,
right,
and then concentrate on seeding rather than always fertilizing first.
Yeah.
So it's something that's been studied. Like that's what they do with the corn. Like you will have we better go take a quick look
20s.
at this machine. So
this is the grandmother's garden version right here. And this is how they did the 20s, I think. So you see one of these for a $5 at a garage sale. snag that up. But this is the farm
Come on
version.
over here, guys, and take a look at the machine up front. Have you seen a deep bander before? It's kind of a tank. You can see it starts off with the residue managers at the front here. They got a cutting coulter and then a great big hole type opener. And in their cases, they're actually deep, sometimes banding 6, 8, even 10 to 12 inches deep. And this is a pretty accepted practice towards a conservation tillage system. You could tell though that it does do a pretty rip up job of where it goes. So we got a couple of closing wheels and then sort of these batter reels in the back just to smooth it all out. And it does a really nice job. You saw in the corn how it cleared the way. Now this is a little bit fancy for our type of agriculture. The other trick is it's on 30-inch rows.
Yeah.
So how can we take a concept like this and do it into our narrow crop grain type production? And so what Mike was talking about is rather than doing all of this fancy stuff, all we're doing is using a stealth opener. So a lot of guys have shank based openers, say on 12 inches. That maybe with the packer wheel in the back, banding in that immobile nutrients, and then because we have RTK, RTX, good, even WAS is pretty decent, but you can follow up on the exact same line and get a little bit of the best of the both worlds. So this is sort of new and it's not really happening out there, but you can imagine we can't squeeze this into a 12-inch row spacing the way it is.
Yeah. Take home message is that, you know, the dryland versus the irrigated, there's pretty massive differences between the two, and managing the residue we saw had kind of the biggest implications on what was going to happen with our corn crops, as well as kind of that hitting that ideal narrow rows and higher populations. So, well, yeah, that's maybe an interesting thing to think about. I think I'm not sure anybody's
Would it last
thrown
3
that
years?
one on
Would
us.
it last 3 years?
Well, it should, because we're looking at, like, we maybe have 15 to 20 pounds of background phos here, and so for something like the canola crop, we're trying to add, I think, usually about 30, and so we 3 times that to 90.
Right.
I don't really think, because we're going to have wheat and then peas after that, I don't think that the canola is going to use up all 90 pounds of phos available in the soil. I mean, that'd be pretty interesting to see.
But in terms of efficiency, I mean, you know, going in every year, I guess that boils down to economics. Like,
yeah, and I think that was another big consideration. So if you can go in and put all that fertilizer down in one pass, one time at a 3x rate, that saves you from having all the logistical implications of having to tank all that around with you when you're seeding later on, right?